In end of 2010, I was asked by a manufacturer to measure a light source, because he wanted to be able to quote things on the publicity details. So I measured the photodiagram, I measured the battery lifetime, measured the power output, how hot it got, all that sort of thing. When I came to measure the colour performance, I was appalled at how crude the mathematics of the CRI is. And then I fortunately remembered some work that was started in the 1970s by these two guys, Bill Sproson and Bill Taylor. They started work in 1970, which was, or rather they made their first report in 1970, which was a few years after the CRI was launched. And they started this work because they were appalled by the CRI as well. They thought this is not relevant for television. They produced 3 reports. The final one was issued in 1988, and in theory they had a system that could have worked, could have been adopted. It was fairly crude by today's standards. It was fairly sophisticated by the standards of those days. But I'm rather glad it didn't get adopted, because it gave me a chance to rewrite it all. So, having discovered how rubbish the CRI was, I dug back into my own archives, found those original reports, worked out what they'd done, started writing software, and have developed it almost beyond recognition. So what we are now seeing as the television lighting consistency index is based on the work that these guys did, but I've taken it a lot further. Like, we're no longer using the colour science of the 1960s, we're using the colour science of the 21st century. This matters because the early stuff is wrong. It really is wrong. Who here has got a colour temperature meter? Do you believe it? Do you use it?
No.
Do you believe the numbers?
No.
Good, well done. You should not believe the numbers. They are all wrong.
Oh, when it comes to kelvins, I do. But,
don't believe it, even when it comes to Kelvin. Believe it if you're pointing it at a tungsten light source or at natural daylight, or maybe an HMI. But not fluorescence and not LEDs. They tell lies, big lies. You will be surprised when I show you just how big those lies get. And you have no clue that it's getting it wrong, except your eyes. Your eyes are a better meter than any meter. And the better meter still is a camera. Proper video camera, like that, well, professional version. Broadcast video camera is always going to do a better job than any colour meter does. So what we have to do is work out how the cameras work and calculate the results from that. So, this is where we start. That's Teddington Studio 1, it's a big saturation grid studio. Awful lot of lights hanging from the ceiling, hell of a lot of power goes into that place. And all of those light bulbs, are all the luminaires are big, really big dustbins, and they have enormous light bulbs inside which consume an awful lot of power, make an awful lot of heat, and generate a little light occasionally. And most of that light we throw away or put in jars in front anyway, so it is a hugely expensive and wasteful way of producing light. Particularly when these are some 10 kilowatt light bulbs I found at Pinewood. They're absolutely glorious, but those are electric fires, they are not light sources. They're 95% heat, 5% light that you want. There is a better way of doing it, but there's a price that you have to pay, as everybody's already told you. LED light sources are not good at reproducing colour. Probably, possibly, maybe, depends on the source. This is an RGB triplet of LEDs. A red spike, a green spike, a blue spike, so there's gaps in between. The standard colour checker chart, you can see natural daylight illuminated across the top, and the LEDs across the bottom. There is no problem with the grayscale. The grayscale matches absolutely perfectly. But the colours are appalling, particularly this poor guy's face. No colourist would have any chance of trying to put that right on a real production. So clearly this is a rubbish way to do it. There are better ways to do it. So how do we work out how to do it? I don't know why I'm missing a bit off the edge of the screen. Oh, well, never mind. Maybe the projector's moved. No, it's not that. Oh, no, never mind. We'll live with that. The technique that the two Bills invented in the 1970s were you take a test light source, the thing you're interested in, and a reference light source, I'll come back to that, and you compare the performance of these two sources when lighting a set of test samples, for example, the colour change now, through a mathematical television camera. There is no real camera involved. It's only numbers. Everything's in software. But we derived the nonlinear RGB signals, which is exactly what you would do in a normal camera, then apply them to a conventional display for television. And that produces the output in XYZ, CIE 1931 values, and we can use those values to calculate the colour differences. That is what the CRI does, except that it emits all of this lot, the entire camera and display. So the real difference is that the fact that we're including the performance of a camera, which is after all what TV does, and what goes in this difference calculation box. And that is one of the big clues as to how we have changed things. The nice thing as well is because we're generating the nonlinear RGB signals in the software, we can output them to whatever the computer display happens to be. Now, if the computer display happens to be a genuine HD monitor, you see the colours for real. So you don't have to rely on the numbers to tell you what the differences are. You can see it for really for live. So it says there, run the software. If I do that, I have to fiddle about a bit. So I won't do it that way. I will do it. Oh God, it's gone away. I was trying to shut me down. Don't shut down. This is the software that I started writing at the end of 2010 and was still writing this morning. I don't think I'm ever going to finish doing this because it's too much fun. Right, that will do. Okay, so let's open file for TLCI. Let's take something that we measured yesterday. Not yesterday, on Wednesday, and calculate the result. There you go. That's the value. That's the output you get from the software. It's normally a sensible shape, but I don't normally work with 4x3 screens, particularly as low resolution as this. I like big stuff. So, this is a representation of the color checker test chart. In each patch, the main area of the patch is lit by the reference source, which in this case is Planckian at 3357. It's a high output tungsten, effectively. The centre part is as lit by the light source itself. So this is how well that ARRI little beast over there works. It's got a value of 80 on a scale of 0 to 100. Now the TLCI also has a scale of 0 to 100, except that it can go negative. We measured one source sometime over the last few days. I'm not going to tell you what it was, but the CRI value of it scored, the TLCI value scored 60, the CRI value scored minus 914. There's not a lot of connection between TLCI and CRI. CRI tells lies, it gets it wrong. This is the spectrum of the light source involved, and that's the reference source we're comparing it with, obviously a tungsten source. Up here, this bit, I think is probably the most useful part, although some people in the industry think that's irrelevant. It's the colorist's advice table. It's a table giving the corrections that a colorist will have to do around the 12 30-degree sectors of a hue circle in each of lightness, chroma and hue. So for the red area, it has to put a little more red lift, increases chromas slightly, little more saturation, and change the hue a little. That's this patch. Down here, the green cyan, we're talking of this and this, maybe that. Need a little more correction to the hue, but not to the lightness. So that is possibly a useful table that a colorist can look at to get him started on what he needs to do to the picture. The more pluses and minuses there are in that table, the worse the color rendering is. It's as simple as that. You could just simply add up the number of pluses and minuses and that would give you the score. Except that I've done it in a rather non-linear way in order to avoid going negative. So the value here, the 0 to 100, cannot go outside that range. And they use a non-linearity to make sure that doesn't happen. So all the really good sources are squeezed together at the top, near 100. All the bad sources are squeezed together at the bottom, and we've stretched out the area in the middle, the area of interest. So the scale 0 to 100 the way we think it's going to work is that for a threshold value of 50, which is for a conventional fluorescent tube, for a threshold value of 50, above that, a colorist can get it right. Below it, below 50, he might be able to get it right, but you won't like the results if he does, because it will be noisy in some colors, there will be masking to do, and the process will take a long time and be expensive. Thank you. Yes, correct. Above 75, the correction will be easy to do. Above 85, he won't bother doing any correction at all. It will be so good. Now, in order to get performance like that in a CRI, you need to be talking about 93, 94, 95. So we have shifted down all the decision points. We've stretched the scale out so that it makes sense. We're not cramming everything together near the top as the CRI does. But that's a fairly useful way of showing things. Let's take a look at, and this is the user mode of the software. If we look at the CRI for the same source, you can do that as a calculation here. There's the same light source. CRI of 91. TLCI says it's 80. That says it's 91. The higher the two scores, the more they are likely to be similar to each other. But there is always going to be a difference. You're very rarely going to find CRI and TLCI giving you the same number, because they mean different things. The CRI is trying to accommodate the way that we see it's human eyesight. The TLCI doesn't do that. It uses the TV channel to do some other calculations for you, like the white balancing. Because a television camera will always white balance to the illuminant. So that's what this is doing. It's what the TLCI does. The CRI doesn't do that. It uses a mathematical approximation of how the eye rebalances. And that approximation has really been sneered at by the colour industry for quite a long time. And there are better ways to do it than the CRI uses. But it's too late to get anything changed in the CRI. It's all written down, it's fixed. And the CQS didn't provide a significant improvement over the CRI as far as I'm concerned. It improves some things, but doesn't go anything like far enough. And apart from that, the CIE, when they were asked to vote on it, had one vote against, therefore it was dropped. So the CQS is not an international standard. The TLCI is, because it's an EBU standard. As far as I'm concerned, that makes it international. I hope. But it's up to you guys to prove this and make it happen. I'll come to that. However, it doesn't just stop with the TLCI, because a few months ago, Jonathan Harrison, I happen to know he deals a lot in lighting, does a lot of training. He said, can't we get this software to do something different, something a bit more useful to the individual user? Because what we've done here is generate a system that manufacturers can use to get their lights right, to make their lights as good as they can be got. But for the guy on the shop floor, the guy out making real programs, the gaffer, he needs to know what he's got to use. Will all lights match each other? So, I modified the software slightly. The first public announcement of this was on Wednesday in Aarhus, and you're the third lot of people getting to hear this. The EBU doesn't know about this yet. It is not a standard. Well, it will be, but it's not formal standard yet. Called the Television Luminaire Matching Factor, TLMF. What that does is another little dialogue. Here you can take a light source and another light source as a reference. Let's try that. That 3200, yeah, it must be. So these are two Arri light sources. I measured these 2 days ago, whilst doing this. So these are real recent measurements, and I know they're right. If we take those two light sources and calculate the TLMF, they have a score of 79 if you use them together. It's close enough to the 80, 85 threshold. So if you use those two light sources together on set, you won't have to do any colour matching. They will match each other in terms of colour performance. And you can see why they match. Because again, we have the same presentation, the reference colour in the outer and the test illuminant in the middle. They match each other well enough not to worry about. You can mix them. Does that sound useful?
Yes.
All right. What we would love to do is to get a manufacturer of a small spectroradiometer to include this software in their software so that it all comes in one piece, handheld. Now, there's one firm that already does that for the CRI. UPR Tech, the MK350, already does the CRI in a handheld unit. There's a little LCD on the front of it. So there's no reason why they shouldn't incorporate this software as well and do TLCI, so that the gaffer can point at one light source, go click, point at another light source, go click, and see what the comparison is. Does that sound useful?
Absolutely.
Right, good. Now it's up to you to go and talk to people like UPR Tech and say, please can we have a meter that does that? Because you've been told it can be done. And they can have the software for free if they want it. So I'm not keeping secret how I do this. I mean, there's no point keeping secrets like this. There's no point being a smart arse if you don't jump up and down and shout about it. People have got to know how to do this. But here you can see the spectral shapes of the two light sources. It's no surprise that they perform quite similarly. You can see that intuitively, that they're going to be pretty good. But to know what the numbers actually are is really rather nice, particularly since you can now see the only area that is a problem is in the cyan to blue area. That and that, maybe that. All the other colours are fine. Not much to do. So you could live with that.
What about the numbers that we calculated out here? Could they work together with a grading program?
Absolutely.
Yeah, that would be very
If we can find a standard way for this software to talk to the colour grading program, then we can plug that table straight in. And that will give the colourist his start point.
Exactly.
He can then do what he wants to do to make it look how he likes it. But that will take an awful lot of the initial experiment out of it. The problem is, how many different grading software packages do you know?
a lot.
Every NLE that I've ever come across has got grading in it, and none of them have an input for it.
No.
So we would need the industry to standardise on
Exactly.
an input
Need a new
format
standard, I
for
guess.
this data.
Yeah.
It's not going to happen.
Okay.
So the best we can do is give that as written advice and say, that's how it works, try it. This is the user version of the software. It's free. You can download this from the EBU. Well, you can't download this because I was still adjusting this morning. But the software in the latest release version is on the EBU website, and you can download it and use it. But you need a spectroradiometer. I'll come to that later. If you pay a little extra, which means if you give me some money for doing this, you can have the engineering version. Now, the engineering version gets you to lift the bonnet and see what's underneath, play with the nuts and bolts. And so you have a rather small dialogue which controls all the parameters. There it is. There are a few parameters you can play with, but if you play with any of those parameters, you don't get the numerical result. You only get the numerical result if it's using the default parameters. Actually, you can cheat, you can get the numbers, but you have to work for it. So you can see that here we have, for instance, that's the light source that I've selected. Here is the luminaire that we're comparing it with. I've selected the TLNF up here. In this reference illuminant, I can have absolutely anything. The test samples can be several different sets. For example, you can load in a test chart of Lee lighting gels and use that as the colour test chart. Does that sound handy? Mm-hmm. Right. The camera responsivity curves, I'll come to that later. We've got a matrix, gamma corrector in the camera. You can have lots of different gamma curves. For example, these are the ones I know of, and I know there are more, but I don't care because these are the important ones. And if you don't like any of those, you can roll your own. You can put the numbers in and create your own equation. Display gamma can be pretty well anything. The display primaries can be anything. And the colour difference system, there are 5 CIE standards there. They're all listed in CIE Tech 15, this document, which costs you about $160 if you have to buy it from the States. It's a real pain, that is. I mean, buy an international standard. How the hell does that make sense? The bottom 3 are based on a TV colour difference metric which uses the nonlinear RGB signals. And I thought, let's try it. Let's just see how good TV is. And it's surprising. It's actually better than some of the CIE metrics. Now, that was a big surprise. Final thing, you get to choose down here is the equation which relates the delta E star, the colour difference value you get from the measurement, to the number that we quote from 0 to 100. Because the delta E star value, the colour error, when that's 0, we get 100 for the QA value, obviously. If there's no colour differences, we give it 100. So how do you scale the delta E star values in an equation to produce this scale 0 to 100? The CRI uses that equation. And that's why we can have negative values, because it's 100 minus a number. So if the delta E star values are big, you can have huge negative values, which strikes me rather stupid. So I invented this equation. Come on. It can't ever go negative, but it's got power laws in it. So the value K is the value that produces 50%, and the power law P describes the curve, how nonlinear it gets. These two values seem to make sense, so that's what we've adopted. If I now select PLCI instead of CRI and reset the parameters, the dialog closes, reopens with all the right numbers in it. And now you can have, for instance, any reference luminaire you like. Roll your own again. So this is completely open to play with, but you only get the TRCI value if everything is standardized. There are some nice things that you can get in the engineering mode, like lots of diagrams. That's the white point. This is the spectrum locus, the range of colours you can see. That's the display triangle, and each purple blob is where the reference illuminant places one of the colour checkered colours. The cyan blob is where the test illuminant places it. And you can see that the only problems we've got here is really in the magenta areas and down here towards blue. And if you want to know how significant that is, you can add other things just to make life interesting, such as the McAdam ellipses. And what McAdam did in 1942 was measure his own eyesight. He set 40 different test colours and then adjusted a colour match until it was just visibly different. So he detected the sensitivity to small changes around 40 colours. And these ellipses are those results. So we can see here in magenta, we're not particularly sensitive to saturation changes, but we're hugely sensitive to hue. So that is a big visible colour difference. But up here, in red, we are not at all sensitive to saturation, but fairly sensitive to hue. Unfortunately, that red is only difference in saturation. So you can actually get a good visualization simply from this graph of what the pictures are going to look like. And I've been using this as a helpful tool to design the algorithm to make it make sense. It took ages. And there's lots more tricks you can do. It can't whistle Dixie or make the coffee, but it's getting close to that. Yeah, it's one of the nice things. If you've got a chromaticity diagram, as soon as you go inside the TV gamut, you can actually see what colour is at that point.
What's the inner triangle? Is that the gamut or?
Colour gamut of the TV system.
Okay.
Yeah. Red, green, blue triangle.
Yeah.
So, lots of things you can play with. But this is only in the engineering version. Right, I'm going to come out of this now and go back into the PowerPoint because time is getting on. Let's close itself, so I'll have to go back to okay. So that's how the software works. Right. Now, because there are lots of little boxes that you can fill in numbers in the dialogue, I expect you might want to know how we came by some of those specific values. Start from the display. The display primaries, the chromaticity coordinates of the display, are specified by the ITU. We know what they are for HD. It's written down as a standard, ITU 709. Same thing for the gamma curve. It's power value 2.4. I would argue with that. I'd say it should be 2.35, but that's because in the 1990s I measured around 20 grade 1 monitors in research, and I found the gamma curves were 2.35 plus or minus 0.05. So they range between 2.3 and 2.4. I can accept 2.4. Doesn't actually matter all that much, as you'll see later. The gamma correction here, again, that's standardized by the ITU, recommendation 709, specific equation for HD. Every HD camera has got that equation built in. Nobody uses it. The reason nobody uses it because as soon as you come to a camera, you set up the standard curves, standard conditions, you look at the pictures and I don't quite like that. You start playing with the knee and with saturation and black lift and all the rest of it. So we know we're going to distort it, but there is a standard, so that is the one we have to use. There is no point developing an international standard like this that doesn't use other international standards. We have to standardize. So this is not an attempt to mimic the real use of real cameras. This is an attempt to mimic what the best use of a laboratory setup camera could do. And that's where the problem comes with these two boxes, because there are no standards for that. There aren't even any real measurements. Well, there are, but they were done in the 1970s. I mentioned, I'll come back to that, I mentioned color temperature meters. This is something I got from KinoFlow because I measured some of their tubes a few weeks ago and I got results which I didn't expect. 3 types of tube, KF 29, 32, 55. Does anybody know what those numbers mean? What do you expect them to mean?
The Kelvin.
Yeah. So you would think that KF 32 means 3200.
Yeah.
KF 55 means 5500. You would expect that, wouldn't you?
Yeah.
That's so would I. That's why I was surprised at the results, because I didn't get that. The KF32s came out to be 3065 or thereabouts. That's okay, that's reasonable. The KF55s came out at 7800. Is anybody surprised at that? I was. So surprised that we measured many times and then went outside with my spectroradiometer and measured the sky. And I got an 8000 for that, and the Kenko CCT meter said it was 7600-ish. So my kit was agreeing with a CCT meter on a blue sky, but not on fluorescent tubes. So what was wrong? So I sent all my measurements off to KinoFlow, and they came back saying, you're right. And the reason why they say you're right is because they also know that CCT meters tell lies. And in fact, KinoFlow have written a paper, which you can get as a PDF, which says CCT meters tell lies, particularly on fluorescence and spiky spectra. So this is fluorescence and LEDs. LEDs are spiky spectra. So if a big spike or a big hole in the spectrum, you're going to get wrong results. The meter's not going to tell you the truth. But if you measure the spectrum with a spectroradiometer, such as this one, which I bought from a Canadian firm for $600, okay, that's a Fisher-Price type price, and it's a Fisher-Price type performance until you actually do something about it. But this will give you the spectrum, and then you can do the calculation properly and get the CCT right to within about 20 Kelvin. Yes, 20 Kelvin, not 2000. I think there's a reason for doing it this way. CCT meters don't make sense. They did when all we had was daylight and tungsten, but life's changed. So, there you go. Don't believe these numbers unless you know you can. You preferably believe your eyes or what the camera does.
It was actually 5500 kelvins.
Well, no.
You mentioned.
No, the tubes were marked KF55.
Okay, and they were 7.
But the CCT I measured was 7800.
Okay.
And it looked blue. It didn't look like 5500, which is a warm
exactly
daylight.
Like you saw it.
Yeah, 5500 is like looking at a direct sunlit scene. 8000 is like looking at the blue sky that is behind that scene.
Okay.
Yeah.
Yes. Okay.
Mm. These curves are, this is your curves?
No, that's KinoFlow. Nothing to do with me.
Oh.
I downloaded from that website. That's why I did a screen grab and say, this is not my measurements, this is KinoFlow.
I believe that the blue peak would match different cameras, and some cameras.
Who can tell? Yeah.
And so it could.
Who can tell?
Very different results.
Absolutely. Anyway, so all this is written down. EBU recommendation R137 says if you want to measure the colour performance of a luminaire, use this technique. That's what recommendation 137 says. All of the mathematics is in the EBU technical document 3355, and there's about 60 pages of it. It's not an easy set of maths to do, but if you can write code, you can do it. If I can do it, anybody can. In fact, 3354 is some subjective tests that we did, and 3353 is the result of measurements of cameras that Per Böhler at NRK did early last year in order to find the responsivity curves of a typical HD TV camera. So, didn't have that data when we started doing this software. So back in early 2011, when I was starting to write software, the camera curves that I had available to me were these. I had 5 sets of Plumbican tube cameras measured in the 1970s and 80s, 3 sets of CCDs measured in the late 80s, early 90s, and these are film stocks I downloaded from the web. Because you can download a PDF, you can trace the curves off, you can work out what it is, it's fine. And I found for a particular really nasty, cheap Chinese single white LED that changing the camera curves between all this lot produced only a change of around 1.5 to 1 in the results. So we know it's not hugely critical on the camera curves, but it does change with the camera curves, so it's important that we get it right. And because it does change with the camera curves, we can't use the results from any one specific camera, because the other manufacturers will say, why didn't you use ours? We can't use the results from only one manufacturer for the same reason. So the best we can do is measure a lot of cameras from different manufacturers and produce some sort of statistical mean from them, an average typical standard camera. So that's what we did. Per, when we found that we had to do this in March of last year, emailed me to say, I think I haven't thrown away the kit that we used in the 1970s. So he rummaged around in the cupboards in the basement at NRK and he found all the old equipment. Hadn't been switched on for over 30 years. Dug it all out, plugged it all together, switched on, and it went bang. One power supply exploded. So he climbed inside the power supply, found the electrolytic capacitor that looked like a dustbin, changed that, and everything worked. So fine. So we got all this kit going. But this had been last used in around 1969, before the invention of the PC. So everything is hand cranked, everything's done by hand. That little black box there has got a light bulb in it. The next box has got 2 lenses to produce a collimated beam. The next box, this cream one, is what's called a monochromator. It's a device that makes monochromatic light. Shine white light in, and there's a slit that produces only one wavelength. This box is just a baffle with a piece of diffusing glass on it. So here it's set to around 550, 560 nanometers, and it's making green. The hole isn't quite circular because there's a photo cell sitting over part of it, so that we can use that as a normalizer, so we know the power output. Here's the camera looking at it. There's the signal it sees, there's the signal it sees, and that's the parade waveform. Right, so Per sits at the desk here. He winds a handle on that by hand to advance it 5 nanometers, waits for everything to settle down, reads the value on this microammeter, which is reading the current generated by this cell, 0 to 15 microamps, that's a hell of a microammeter, writes that down, then looks at this and measures the RGB values. So obviously we have to be able to turn off the matrix and the gamma correction in the camera. That means we cannot use anything like this, or DSLRs, or a lot of the single sensor cameras. It has to be a top-end professional camera. That's fortunate because those are the ones that matter, as far as I'm concerned. The coffee cup is absolutely vital. You can't do this without caffeine. We measured around, I think it's 9 or 10 different camera models. Some of them we measured 3 or even 4 different camera bodies because we suspected the results. And each camera was measured at least 4 times. So there's a heck of a lot of data processing. That's why this took about 2.5, 3 months to do. If this had been automated, we could have done it in about a week and a half. But it would have taken longer than that time to automate it. So it was actually worth Per sitting down there and actually winding the handle and getting really bored and making mistakes and doing it again, and all the cross-checking that we had to do. So the monochromator, the box in the middle, this is my illustration. This is in the book that I wrote for the EBU. Light comes in parallel beams through an entry slit, bounces off this mirror onto a parabolic mirror, which makes a parallel beam of light onto the grating. The grating has ruled lines which go vertically, and it's pivoted at this point, and you can rotate the entire grating. So the rainbow that it makes is reflected off this second parabolic mirror and out through the slit, which selects only one wavelength. Nice and simple, except that it costs around 5,000 sterling 20 years ago. God knows what they cost now, but I certainly can't afford one. So it's fortunate that that little beast over there, which does the same job, is only 600 Canadian dollars. But for 600 Canadian dollars, you get 600 Canadian dollars worth, which isn't much. That's the diagram of pair used in Tech 3353 and in the SMPTE journal article, which we have got published since then. There's the box with the light bulb in it. Little box here with two lenses making a collimated beam. The monochromator itself, output lens through the slit, diffuser here, out to the camera. So far, so good. But this firm, Ocean Optics, makes a huge range of little spectroradiometers, some of which are good and some of which are not so good. And so we can now do everything much more quickly than in those days. But we can't do this job on a camera because we don't need this as a spectroradiometer. This is for measuring light. We need to split light. And for that, you have to have what's effectively a tunable filter. And so far, nobody's done that in small, because you can't. You do need the moving parts inside. Right, anybody spot the deliberate mistake in that picture? You do realise this is a test to see if you're still awake. What's wrong in the picture? Yeah?
No coffee in the cup?
Oh, no, there wasn't in the previous one. Now, what's wrong in this picture?
There's red spots instead of coffee.
Yeah, exactly. Yeah. The kit is making a green spot, but the camera's seeing red.
Oh, it's just colorblind.
Well, that's what Per said. Per said he thought there was something wrong with that camera. I thought, well, no, he's recording it. He's playing back a recording of a previous measurement. I'm a forensic engineer. I work out how things could have happened by looking at the result. It's amazing what you can work out in doing that. These are the results he got from the sets of cameras that we measured. So each different colour, each different colour is one specific camera. So I haven't labelled them red, green, blue, but you know which is which. The interesting thing is how similar they all are. The crossovers all happen in the same place to within about 3 nanometers. The slope down this edge is about the same. The slopes down these edges are the same. The slope down here is the same. There are small differences. There is one camera here that goes up to 740 nanometers in this box. In the 1970s, the standard wisdom was no camera should respond up to more than 700 nanometers. This one goes up to 740. So there are significant differences between the cameras. Therefore, this model that we're producing is not representative of any specific camera. It's a generic camera which is typical of the entire class of HD cameras we're using. So the results will not be the same if you put a real camera and do the same test doing the same insetting, but it will be very close. The other thing we noticed, one camera here had this big bulge out to the left. So we measured 3 different bodies, 3 different serial numbers. Many times, got the same answer each time. So it's typical, it's right.
You didn't measure any CMOS cameras?
Yeah,
Or what?
hold back a bit.
Yes.
CMOS cameras are hard. In the green response, this orange curve for instance, goes up here and then has a long slope rise, but this purple one is flat across the top. Also, the green response is fairly broad at the top, much broader than the old Plumbican tubes. We think this is so that they can claim another half-stop sensitivity, because the green sensor is intercepting more light, and it's the green channel provides 70% of the luminance signal. So if you can intercept more light in green, your camera sensitivity goes up. So you can claim greater sensitivity. It doesn't actually wreck the colour performance significantly. It does change it, but it doesn't wreck it. Anyway, so that's the range of different cameras that we measured, which was a big surprise to us because we were expecting bigger differences between them. When I averaged all of these together, what we did was estimate, by guessing within the committee that the EBU had set up, roughly how many each manufacturer had sold of that particular camera for use in HD. And we produced the average, weighting them by the number of cameras. So the cameras that sold most get the heaviest weighting, camera that sold least get a lighter weighting. So we're aiming to produce results which are typical for the way people use high-end cameras, not the low-end stuff like this. And that's the result we got. I dived in a little and adjusted a few values to take out a few little kinks and bumps. So this is not representative of any one camera, it's representative of a whole class of cameras. Notice also that we have this long red response underneath blue and green, and a long green response. We don't see that in any of the 3-chip cameras. That is the result of a CMOS camera. Now we know that pretty well all the high-end CMOS cameras have the same type of curve because they all use the same dyes on the chips. It's an organic dye which covers each pixel, produces the colouring. In a 3-chip camera, the colour separation is done by dichroic filters which are glued to a prism. The prism takes no part in the operation apart from diverting the light. It's the dichroic prisms that make the filtering. But in a single chip camera, the colouring is done by these organic dyes which absorb light on each pixel. So they don't have to fight each other. So you can have some blue light going into the red pixel and some blue light going into the green pixel. And that has a very interesting result. It doesn't ruin the colour performance, but it does make the colour performance better if you turn the matrix off. So in a single chip camera, if you turn the matrix off, you get better colour performance than if you do the same in a 3-chip camera. It also means that when you produce an optimised matrix for any of these cameras, the coefficients in the single chip camera are smaller than they are in the 3-chip camera, so the noise performance is degraded less. That's why single chip cameras are better than 3-chip cameras. I didn't expect that. That was a major surprise. I'm still learning. The day I stop learning, I will give up. Anyway, so that's the standard set of camera curves that we've now got published in EBU Technical Recommendation 3353, written by Per. That's the only one of these documents that I didn't write, but I edited for him to make sure the English was right. There he is, standing in front of the IBC booth that we had last year, talking about everything. I don't know who this guy is. He might be one of you for all I know. I can't remember. I only took the picture. Incidentally, we also got a What Caught My Eye award at IBC, which the EB is very proud of. I'm not proud because I gave the award. I was booked to go to IBC last year. They paid me to go in order to do a What Caught My Eye session. So I spent Friday touring the exhibition with a camera crew, and I visited this stall to make sure that we got some publicity. So I gave us an award. I'm quite happy about that. No point having power if you don't abuse it. The EBU is very proud of that. But I still think they actually deserve this because it needs the publicity to get out. It needs users and manufacturers to know what's going on. And it seems to be working. It's all published in this document. There it is. Note the date, November 2012. And did anybody remember when I said the EBU started the committee work? I'm not sure whether I said it. It was November 2011. So in 1 year, the EBU has gone from forming a committee to start work to delivering a final product. In 1 year. I claim that as a record. I don't believe any EBU activity has ever been that quick before. But remember that the work started in 1970. So it's also the slowest project to do. I'm quite proud of that as well. Because it means we've been thinking about it. You know, it is not an instantaneous result. It's something we know has to be done. Okay, the far right-hand box, the colour difference measurement box, the bit that actually works out a colour difference value. We had 5 different CIE metrics we could use. We decided not to test CIE 1964 because that doesn't measure chroma and hue as colour differences. The later 5 all do, so they could all contend to be useful. These two, CIE Lab and CIE Lab, were both developed in around 1976, which is only 12 years after the CIE 1964 that we are saying is rubbish. And the industry still believes that CIE Lab is a lot better than CIE Lab. Right, so we thought we had to test this. The 3 later versions, CMC came in the late 80s, 1994 for this one, 2000 for CIE DE 2000. I thought DE 2000 ought to be the best because if you look in CIE Tech 15, where all the numbers are for how to do this, it says if you're going to measure colour differences, use DE 2000. The mathematics for all the others is included only for reference. for historical purposes. So the CIE knows that all these others are crap. So how crap are they? We tested. We used my software. We had 3 different light sources, a bad one, a medium fluorescent, and a good one. The bad one was a cheap Chinese 112 white LEDs, and it was only about £3, so we knew it was rubbish. The fluorescent was an ordinary warm white, ordinary fluorescent tube. The good LED had to be not perfect because then all the colour differences would be 0, nobody'd see them. But it had to be good so that it was difficult to see the differences. So we chose a Kelvin tile. So we had 3 different luminaires, 5 different colour metrics, that's 15 tests. And what we did was we set up the software to produce the colour differences that each of these combinations, each of the 3 luminaires produced. Then had 5 tests with the numbers given for each of the colour difference metric. And we asked the observer to mark the numbers. Do you agree with it or don't you? And to make life easy, we simply said compare the performance of, let's say, the dark skin and the light skin, 2 together. If, say, the dark skin scored a delta E star of 2, but the light skin scored a delta E star of 3, and you thought the light skin looked worse than the dark skin, you scored a +2. We agree. If you thought that the light skin was worse than the dark skin, but not very much, or by a lot, you scored a +1. You said, yes, it's in the right direction, but I don't agree with the numbers. If you thought the verdict was the wrong way round, it scored -2. So we're using the EBU 5-point scale. Score 0, we didn't allow, because you haven't tested it. We were forcing an active decision, not allowing a result I don't know. That's not allowed. You have to decide. And score -1 didn't make any sense, because that would mean it was in the wrong direction, but the numbers were right. So that's clearly nonsense. So we used 3 points of the EBU 5-point scale. So +2 means it's perfect, -2 means it's absolute rubbish. And CIE Lab only scores just over half, whereas CID 2000 scores about 1.5. It's better. But the amazing thing to me was how much better CIE Love is. If only the CIE had started on this one in 1964 instead of that one, how good would this have been? Quite a lot better, I suspect, and quite a lot simpler to calculate, because the maths for that is horrible. If anybody wants to write an algorithm to do that, please talk to me. I will talk you around how to read those equations. And I know I'm getting it right, because everybody else is agreeing the results make sense. So, there we go. That was for the 3 luminaires for all of the observers. We used people in Toronto, in Geneva, in Oslo, in London, one in Hanover. And we all got more or less the same results. They average out quite well. But we did include a cross-check, which is switch all the numbers off and show the 3 sets of results again, and ask each observer to mark how big do you think that colour difference is. Pretend you're a CIE colour difference metric. Tell us how significant each colour difference is. And we used that as a source of correlating with their results to see who was reliable and who wasn't. And I was one of the most reliable on a consumer plasma TV set, my TV set at home, but one of the least reliable on an LCD at home. It's nothing to do with me, it's the LCD TV set. But we found that the people all using OLED grade 1 monitors all produced consistently high correlations. They were reliable people. So if we then weighted the results by the degree of correlation, we still got the same shape. There is no manipulation I could do to this data that would stop the E2000 always coming out best. So surprise, surprise, that's what we used. All that's reported in Tech 3354. I said the display gamma doesn't make a lot of difference. Here's the proof. 2.2 is what the NTSC says a TV set is. 2.8 is what the EBU says it is, but they're the same tubes, so clearly somebody's got something wrong. In practice, both have. The measurement techniques were wrong. I proved that in the 1990s. So this is a plot of the colour errors for the 18 colours on the colour checker chart as it changes as the display gamma changes to process range. This colour, the error drops significantly. This one, the error rises significantly. But on average, there's hardly any change at all. It's not sensitive to display gamma. That means you're going to get the same result whether it's a grade 1 monitor with the correct gamma, or a consumer monitor with a lower gamma, or a PC with a higher gamma, or if your lighting condition is different. It doesn't make any difference. The answers are still going to be the same. Is everybody relieved about that? Because I was. I thought, blimey, we made it. We actually got something right. Also, I refused to take a simple average of the colour errors, which is what the original specification of the CRI does. So this is this is a genuine measurement. The CRI takes the average, which is this black line. The third publication of the CRI says you can instead use an RMS value, which is the grey line. Not really all that different. That's not really surprising because the RMS is good at extracting information from signals which are positive and negative going. This is all in the same direction, so RMS doesn't actually make any sense. So I opted for a fourth power average, the red line. And what this looks like is take the average line and throw away everything that scores under that line and take the average of the scores that are above it. So we're placing a higher weighting on the colours that are more wrong. And I defend that because whenever you look at a picture to decide what's wrong with it, you're always going to spot the thing that is most wrong, and that's what gives you the conclusion whether it's right or not. It's not the average that matters, it's the stuff that's worst. We judge things by how well they fail, not by how well they work when they're working. I did think of going up to the 10th power, but I thought that was a bit excessive, because that takes the top quarter. Could have just taken the worst one, and we've got almost the same result. This is a plot of how CRI values on this axis compare with TLCI values on that axis for 78 real measurements of real luminaires. There is hardly any correlation at all, which is a big surprise. And this one, it's actually a candle flame, scored about -20 on CRI, but around 65 to 70 in TLCI. And the reason is because the candle flame is at 1800 Kelvin. That's off the range of colour temperatures for which the CRI is reliable. 6000 is at the other end, and that was the value that gave us the -900 value yesterday. The reason is because the camera can actually colour balance to any illuminant. It's not a problem. So the fact that it's a wildly different colour temperature isn't an issue for this, for TV. But here, let's take this one for instance. Scores nearly 90 on TLCI, but only 50 on CRI. And yet down here, this scores 50 on CRI, but only about 25 on TLCI. There is no straight connection between these metrics. And the reason for that is because the CRI is rubbish. I would stand up in court and say that. I'm fairly sure I wouldn't get sued. Might go to jail, but what the hell? You know, life's too short to worry about everything. So the CRI is not a good measure of light unless the CRI value is very high, at least 90, preferably 95. 95 and above, yeah, it will agree with TLCI, but not lower. It will give you wildly different answers. And here's the same data plotted as a sequence. This is the TLCI scores for the 78 luminaires, and these are the two algorithms for the CRI. Slightly different distribution. If you're not convinced yet, you never will be. Practical spectroradiometry. I'm aware that time is galloping on. If you have to do this, and I'm aware, Peter, I wrote this part almost specifically for you.
Okay.
So if we don't have time to do this, I'll do it later. I'll talk to you later. Yeah, beware. It's hard. Writing the software is not all that easy, but doing the measurements is actually much harder. There's a lot you can do that will make it go wrong. For example, all of these small spectroradiometers have a line array sensor inside, many LEDs in a single line, and many CCD cells in a single line. And each cell responds with a black current. The charge simply leaks when there's no light. And it follows a pattern because the cells aren't all identical. This is like a granular noise, fixed pattern noise in an image. And the way you deal with that is to cap the sensor, exactly the same way you would cap a camera, make a measurement, subtract that measurement from everything else you do, and all these errors go away. So this fixed pattern here, when you do the subtraction, disappears, and all you're left with is noise. So we know that deviations here are electronic noise. So here we can see the difference between DC leakage and AC errors. That's nice. Use the device to measure itself. I said that before. There's my LR1, 600 Canadian dollars from Vancouver. That's what happens if you open it and have a look inside. Light comes in through the slit, off a mirror, grating, off a mirror, onto the line array sensor. But look what's happening over here. It's shiny. It's black anodized aluminium. If you've got a light measuring instrument, the last thing you want to have happening is stray light bouncing around, because you can't believe the results. You can't. That's what I've been saying to you for months. Yeah. You can't believe the results. No. So what do you do about it? That's what you do. This is Pers in Oslo. He painted the inside of his with black paint. A special black paint he got from Albrecht in Germany, which is used for the painting of insides of telescopes. Works quite well, but not absolutely perfect. I've got a pot of the same paint, and that patch is painted with it. This patch is painted with ordinary blackboard paint that I got from a high street hardware store. That is a sheet of ordinary copy paper printed black on an inkjet printer. That's the same paper on a laserjet printer. That's matte photo paper on the inkjet. Which is the most black? Yeah. Mm-hmm. Black is not black is not black.
No.
All blacks are not black. If you can see it, it's not black. But the best you can do with a paint that you can put on is the Albrecht paint. So using that, we've got the flare inside that box down from around 0.8% to about 0.1%. And on a good day, you can get 0.05%, depending on what you're measuring. So that was mine after painting. I'm not as even in the painting process. And eagle eye will see there's a little black mark there where one hair of the brush actually daubed some paint on the mirror, and I've left it there because it doesn't make any difference. It only attenuates the light, it doesn't produce any more scatter. So now if I turn the thing around and shine this laser into it, 650 nanometers, in through the input port, off that mirror, onto the grating, off that mirror there, there's the spot it makes. So this is the line array sensor, blue at that end, red at that end. There's the single spot. But look, there's internal reflections. Internal reflections are going to cause problems. It was only when we looked at the part number on that sensor we realized what these problems are. That sensor is the working bit of a barcode scanner. It's designed for cash registers in supermarkets. Now I thought we've got another problem. I now need to do some more measurements. So I did. Oh, incidentally, that's pointing LED, white light, single white into it. So there's the blue end, there's the red end. Look, there's another spectrum up here. Another copy of that spectrum. It's a second harmonic. It's got harmonic distortion on the grating. Note also, you can see a lot of light on this grating. So it's not just directing all the light in the right place, it's scattering. That scattered light produces flare if you don't absorb it. This is not easy. Things you have to be aware of. Anyway, so the second thing I did was to have a look at the diffuser that comes on the end of the fibre optic. When you buy these things, there's a fibre optic cable, like so, which has a little rubber cap on one end, which you take off, you just pull that off, and that gives you access to the fibre. Don't do anything with that, please. It's calibrated. Yeah. And the other end has a diffuser on it, which is a little tube with a piece of frosted glass in the end. The object of that exercise is to increase the viewing angle, because the viewing angle of the fibre is only around 5 degrees wide. It's very narrow. It's very hard to point it in the right direction. So we need something that will take light from a lot of different directions. So I needed to know what's the polar diagram of this. So I measured it. It's amazing the things you do in the dark, in a cold winter's night in your garage. These is two of the diffusers that came with this device. That's not one of the LR1 diffusers, that's an Ocean Optics one. And they're roughly circular, but they're different. And they've got a wavelength response, different wavelength response. You get more response at red than at blue, even straightforward. So you get a different spectral capture if you take the diffuser off. So you have to calibrate it twice, once with the fibre and once without, depending on how you're going to use it. Also, if you go off axis, the colours change. This is not a good idea. So I went to Ocean Optics, and instead of the $25 that the one they supplied with the LR1, I bought that one for £81. There's its curve. Much, much more circular, so it's much more like a proper diffuser. And there's hardly any difference in the RGB response. So the wavelength response is good. And this is a block of PTFE that John Emmett in Teddington turned up just to make one because he hadn't got a diffuser. And it's rubbish. You can't con this, you can't do it the cheap way, you've got to do it the right way. Then I started looking at linearity, because as soon as I found out that the sensor belonged inside a cash register, I thought, hang on, this is not necessarily a good idea. So I measured a tungsten light bulb. In fact, it's a calibrated light source. I just measured a tungsten light bulb and changed the integration time in the spectroradiometer from 10 milliseconds up to 60 milliseconds just to see what happened. And this is the curves I got. That's 10 milliseconds, that's 60 milliseconds. Well, obviously it's starting to flatten at the top and you're getting some nasty ripples in it. So how the hell did that happen? It clearly isn't the light level that's going, it's the light level's constant. I didn't move anything. It's only the integration time of the sensor that's changed. So the way to sort this out is to let us say that this value, the 40 millisecond curve, is a standard, and we'll try calculating the ratio of that to that, and that to that, and that to that. See how they relate to each other. And that, in the next slide, should tell us how linear the device is. So clearly the 10, 20, 30, 40 millisecond curves are all linearly related to each other. God, I haven't had enough to drink. At 50 milliseconds, it's slightly bent. And at 60 milliseconds and above, it's grossly bent. What that means is that somewhere between 40 and 50 milliseconds is the linearity limit. So if you go back to the previous slide, somewhere between there and there, it stops being linear. Well, there's a scale of 0 to 16,000, which is the numbers that the device generates. So we can actually say that if the signal that you're looking at on screen goes above that level, it's non-linear. And up to this level, it's still linear. And somewhere in between is the limit. Between 10 and 11,000. So if the exposure that you produce in that device is more than 10 to 11,000, you will get wrong results, guarantee it. And I do not know if anybody else who's bought one of these will have the same problem. They have to measure each one in turn. So what Per Bowler and I are going to offer is a commercial service to anybody who's got one of these. We will take it apart, we'll paint it black, and hopefully not paint the wrong bits black, put it back together, do this experiment to find out what the linearity limit is, then calibrate it from a specific source and send it back. I haven't agreed with Per what the price is going to be for this yet, but since I've retired and he's going to retire in about a month's time, it's not going to be high, it's a hobby. Nevertheless, it's not a hobby we're going to do for nothing. We're going to want something out of it, particularly the post and packing. So there you go. We have flare level problems. We have a second order harmonic problem, which means if there's light down at say 200 nanometers ultraviolet, it's going to show up at 400 nanometers in the wanted spectrum. Stuff you need to know about. Oh bugger.
Can this be the reason why we got low values for tungsten light
easily
and high value
yes.
CI?
Yes.
CI
You will.
Because we had my name is Finn. We had the writing about
yeah.
And it was very confusing
yes.
to have a tungsten light.
Yes, that's it.
Where you gave a low value result.
Yeah.
When
and you got a high one.
Yeah.
That's right. That's the reason. The linearity. Oh dear.
It becomes better because it was.
Yeah, I know. I was really worried.
So confident, you know.
Absolutely. I was really worried until I found this. I thought, that's the reason. And from then, since accepting this and setting a rule that no measurement goes above 10.5 to 11,000, the results that I get are now agreed on by Kineflow and Cree. So I'm getting the same spectrum. So I can make that work as a professional device. But it isn't, it's a toy. If you want to do professional results, either have this worked on and accept that there are limits and obey those limits every time, or buy a better one. And the better one started around $3,000. I've ordered one. I can't live with just that. I've got to have a means of cross-checking.
Can I have one question?
Yeah.
The curve in the right left side.
Yeah.
What does it refer to, the numbers?
Oh,
And you just lost with that?
but these numbers, since it's a digital device,
Yeah.
there's an ADC on the output of the device. It's 14 bits. 2 to the power 14 is 16,384. So there's 16,384 possible signal levels.
Okay.
But you can only go up to about 10.5, maybe 11,000 before it goes non-linear.
Okay, I understand.
It's clipping.
Yeah.
The sensor's got a gamma in it. And for a sensor in a barcode scanner, that makes sense, because you don't want it to saturate. All you need to know is it a 1 or a 0. But for this, we expect it to be linear, and it's only linear over part of its range. Let us hope that the more expensive one I'm buying is better. But you can guess what I'm going to do first thing, as soon as I open the box. I'm going to measure the linearity, see how much better it is. Okay so far? Good. Calibrating. Calibrating process means you have to shine a standard known spectrum into the spectroradiometer and make a reading of it. And the known spectrum will come with a data table which says what the spectral power distribution is. Now you have two measurements which you can use in the equation in the calibration process to correct for any other measurements you make. This is a box that Per found again in a big cupboard in Oslo, made by LMT in Berlin about 35, maybe 40 years ago. He opened it up and again had a look at the electrolytics, replaced one or two, switched it on and it works, but we don't trust the calibration because it's too old for that. So he bought a spare ball as well, and he shipped it to IRT, who are doing a calibration on it this week that will go back to Oslo and become the EBU's reference standard. We are not sure where it's going to live. It theoretically ought to live in Geneva, but I don't think there's anybody competent to operate it there, so probably stay in Oslo. But I can't afford one of them. I mean, look at it. We asked NPL in Teddington what would be the price to recalibrate it. After a lot of poking, they came back with an email saying, well, we only calibrate sources like this twice a year, in April and October, and it will be £3,100 to calibrate it. So I thought, you've got to be joking. So I went out and bought one of these for just over 100. Ocean Optics calibrated light source. There's a tiny little lamp in there, and a diffuser and a tiny little lens. So the diffuser on the end of the fibre optic cable plugs into that port and places the diffusing glass at exactly the focus point of the lens. So if you know the spectrum that this is producing, you can make the measurements in this, and it's portable. Nice little fan there to keep it cool. And it's okay for about 50 hours before you have to recalibrate it. So anybody can afford this. So what we're going to do, when we get that bit back from Oslo, we're going to calibrate that against it. So we'll have a standard source, then we'll have a portable source. So there's the little beast that I bought from Ocean Optics. And Ocean Optics also make, this is not a sales pitch for Ocean Optics incidentally, because there are lots of other companies, it's just the one I happen to know. They make this beast, which is the one I've now placed an order for. And that is $3,500. I've got a bit of a price reduction on that because I bought other stuff from them and they want to sell kit, obviously. And at that point, I'm going to stop. Any questions? I'm aware that I've overrun by around 25 minutes. And you're always going to. No, don't clap, just throw money. Are you happy now?
Yes, thank you.
You now know why I said please hold back.
Yeah.
I don't know what the answer is yet.
Yeah. But it constantly was foolish me with these things. So I'm glad that you...
Yeah, you can get lots of different answers and none of them are right. It's only if you know exactly what the limits of the device are you can get an answer you can trust.
Yes.
Now we know.
Yeah.
All the explanation you've done here, do you have that in writing somehow? I mean, I could spend some more time.
Ooh, yeah,
sure.
Yeah, I'm sure you could. Yeah, I am writing a paper called Practical Spectral Radiometry. Most of the third part of this is in that paper already.
Okay.
There will be more. Once I get the Ocean Optics one, I'll check that in the same way. So we will then have two spectral radiometers we can compare. But I am not at all sure that any two identical bodies will perform identically. You have to measure every one to make sure. I am horribly cautious. I've lived in a world of research engineers where you stand up and say things in public and you know you've got to be right. The only way to be right is to measure everything. cross-check. So I'm not going to stand up and say they're all the same, unless I know they are. But yes, there is a paper I'm writing. It's about 2/3 done. And when I get the new beast and the calibration done properly, then we'll be happy. Incidentally, I know that the calibration data that comes with this is wrong. There are mistakes, because you can see it in the results. If you know what you're doing, for example, let me show you a measurement of tungsten fitting. Tungsten ring there. It will be the sterilite measurements. DODH4. Let's show the TLCI report. Oh look, it scores 100. It scores 100 because it's tungsten, and this is a measurement of tungsten comparing with a theoretical tungsten. That really means that I've got the measurement right, mostly. But look, I haven't quite got the measurement right, because tungsten light bulbs don't have that crinkly and that crinkly bit. That's where the calibration data for the calibration source is wrong. I can see it's wrong, but I'm not going to correct that until I've got a proper calibration source to compare it with. Then I can produce a proper calibration for this and know that we get it right. Incidentally, although it says it's 100, it isn't quite 100, because we use rounded numbers. One option you get in the engineering version is to look under the bonnet at the calculations and see the actual numbers. So here it tells you what the test and reference sources are, and then for each colour patch you get the delta L star, C star, H star, so changing errors in lightness, grayscale, errors in chroma, saturation, errors in hue, and the rounded up figure. And this value down here is the Q figure that we're going to call. So it isn't 100, it's 99.994. That's 100.
Because you couldn't really see the difference with your eyes.
You can see a change of 1 to 2 in the Q value. The change of the TLCI Q value. You could, if you have two lights with a difference of say a 90 and a 92, you will just about see the difference.
Yeah.
Or 90 and an 88, you'll just about see the difference. If they're the same type of light source. If one's tungsten, one's a fluorescent, you will easily see the difference because the spread of colours will be wrong. There will be a different mix of errors, but they'll all be fairly small. Are you convinced? Good. Lunchtime.
Yeah.